Sir Isaac Newton's contribution to our understanding of gravitation was profound. Sir Isaac Newton's input was pivotal. He realized that the motion of the planets and that of falling objects are two aspects of a single phenomenon. Newton used this insight and his law of gravitation to formulate an explanation of the motion of planets and of falling bodies. Newton's law of gravitation states that every particle in the universe attracts every other particle with a force F that is directly proportional to the product of their masses m1 and m2, and inversely proportional to the square of the distance of separation r. The gravitational force is one that acts at a distance, and it exists between particles, regardless of the medium that separates them. The proportionality symbol can be removed if a constant is found that fits experimental data. The constant needed in this case is g, the universal gravitational constant. So, Newton's law established that the gravitational force F between two objects of masses m1 and m2 is equal to g times the product of m1 and m2, divided by the square of the distance r between them. Cavendish found the value of g experimentally. In order to find it, Cavendish suspended, by a string, a rod with two small masses on its ends. He then placed two stationary heavier masses in the proximity of the suspended masses. By determining the amount of twist in the string for different masses of the heavier stationary bodies, Cavendish was able to find a value for the gravitational constant g of 6.67 times 10 to the negative 11th newtons times meters squared per kilogram squared. Newton's law applies to every particle. For extended objects, Newton's law still applies, because we treat extended objects as if all their mass is concentrated at their centers of mass. Let us do an example. If everybody is attracted to everybody else, then what is the attractive force between two students of masses 50 kilograms and 75 kilograms sitting 1 meter apart from each other? Correct. Earlier, we discussed the fact that the gravitational force is a force that acts at a distance, and that such a force exists between particles regardless of the medium that separates them. We can also consider this phenomenon using the field concept. According to this concept, an object of mass m modifies the space around it, creating a gravitational field. Any other object placed in that field will then feel a force of gravitational attraction. The gravitational field is a vector field, in which a vector corresponds to each point in the space. For example, let us look at the Earth. Imagine the Earth as an isolated mass. If an object is brought near the Earth, a force of attraction is exerted on it. The direction of the force points radially in towards the center of the Earth, and the magnitude of the force is mg, where g is called the acceleration due to gravity. So every point in the space around the Earth has a corresponding vector g, which is the acceleration that a body would experience if it were located at that point. This vector g is called the gravitational field at the particular point. The gravitational field is defined as force per unit mass at any point outside a massive object, or g is equal to force divided by mass. According to Newton's law of gravitation, F is equal to the gravitational constant, capital G, times the product of masses m1 and m2 divided by the square of the distance r between them. By placing this value of F into the equation for G, we obtain the equation G is equal to capital G times m1 divided by r squared. In this equation, m1 is the mass of the Earth, and r is the distance between the second mass and Earth's center of mass. Note that G is a vector, and that its direction is always toward the center of the Earth. Also note that the strength of the gravitational field is independent of the mass that is placed at that location. Let us see an example. Find the value of g that the Moon experiences due to Earth. The Earth-Moon distance is 3.84 times 10 to the 8 meters. The mass of the Earth is 5.98 times 10 to the 6 meters. Newton's law of gravitation was stated for particles. However, we can extend it to spherically symmetrical objects. For a spherical shell, if the particle of mass m1 is located at a distance small r outside a spherical shell of radius capital R and mass m2, the spherical shell attracts the mass as if all the mass of the shell were concentrated at its center. If the particle of mass m1 is located inside the spherical shell, then the force on it is 0. This graph shows that the force on particle m1 when it is outside the shell m2 is equal to the gravitational constant capital G times the product of m1 and m2 divided by r squared. The force on m1 is 0 once m1 is inside the shell m2. If the particle of mass m1 is located at a distance of r outside a solid homogeneous sphere of radius r and mass m2, the solid sphere attracts the mass as if all the mass of the sphere were concentrated at its center. If the particle of mass m1 is located inside the uniform solid sphere, then the force on m1 is due solely to the mass m2 prime contained within the sphere of radius r, where r is the distance that separates the particle m1 from the center of sphere m2. Newton's law of gravitation applies with masses m1 and m2 prime. Newton's law of gravitation applies here when the particle is outside the sphere. In this case, the force of attraction on the particle is equal to the gravitational constant capital G times the product of m1 and m2 divided by r squared. When the particle is inside the sphere, Newton's law applies to the particle and the portion m2 prime of the mass of the sphere with a radius r, representing the distance between the particle and the center of the sphere. Here, the force of attraction on the particle is equal to capital G times the product of m1 and m2 prime divided by r squared. If a particle is located inside a solid sphere of density ρ and radius capital R that is not uniform, then the mass m2 prime in the last equation is equal to the integral of ρ times dv, with the integration taken over the volume of the dotted surface of radius small r. Let us do an example. Consider a uniform sphere of mass 10 kilograms and radius 1 meter. Find the magnitude of the force on a particle of mass 20 grams located at point A, 5 meters away from the center of the sphere, and a particle of the same mass at point B on the surface of the sphere. Try again. Try again. Correct. Now let's see what the gravitational pull is on an object inside the sphere. What is the force on a particle of mass 20 grams inside the sphere 0.4 meters radially inward from the surface? Correct. First, let's determine the mass m2 prime of the sphere enclosed between the particle and the center of the circle. Because the sphere is homogeneous, m2 prime over m2 is equal to the volume of the enclosed sphere over the total volume of the sphere. Since the volume of a sphere is 4/3 times pi multiplied by the radius cubed, m2 prime over m2 is equal to the ratio of the cubes of the radii. The mass m2 prime of the sphere is thus given by the ratio of the cube of the radii multiplied by m2. From Newton's law, the gravitational force on the particle inside the sphere is equal to capital G times the product of m1 and m2 prime divided by r squared, where the radius r represents the distance between the particle and the center of the sphere. Substituting m2 prime from the previous relation and simplifying, we find that the force is equal to G times the product of m1 and m2 times the radius r divided by the radius of the sphere r cubed.